All right, let's get started. So our paper session is called Neural Denoising in Motion. And the first talk in the session will be given by Nikolai Hoffmann, who is at the University of Erlangen-Nuremberg, and also this work was done joint collaboration with NVIDIA. Yeah.
All right, thank you. So the work is on denoising, as you can probably all read, and I'll try to get into the topic right away. So the overarching goal of our work here is we want to realize unified light transport using path tracing and as real time as possible. And in order, one stepping stone to do that, we already heard we're pretty good when dealing with triangles, right? But another stepping stone we need to solve in there is volumes, right? So we need some sort of representation for volumes. We need to be able to handle volumetric light transport, either like the volume shadowing the scene or also maybe even the volume lighting the scene, right, for emissive volumes. And since volumes are quite hard to render, as we all probably know, we need a lot of samples for them to converge. So in order to make it real time, we have to lean on denoising quite heavily. And what I want to talk about today is how we can make denoising work for both surfaces and volumes in a single scene. So first of all, what happens if we just take the state-of-the-art denoiser, right? So we have the input on the left, which is 4 samples per pixel, and we have a reference rendering on the right, which is a lot of samples, in this case 64,000. And we want to apply a denoiser to try to get as close to the reference as possible. And there's 2 approaches usually. You could use just base the denoiser of the color data, and another trick is to use feature guides, for example, normals, depth, whatever you can come up with. And if you just use an existing neural denoiser and you apply it to color data, so without guides, it's very blurry because the sampling is hard, you have a lot of noise and then the signal, so you get a very blurry result, right? But if you use guides, on the other hand, you get a pretty sharp result for the surface part. It looks quite nice, you get some detail. But now we start to see the background for the volume, right? Because if the denoiser is not really able to resolve certain pixels, it tries to rely on auxiliary features. Now it relies on normals, but normals for volume are not defined, so you start to see through the volume, which is just not what we want. Right. So we need to deal with this problem, and for that, I want to go through a little bit of a background. I'll very briefly go over the ray tracing pipeline. What I want to show here is if we shoot a ray into the scene, we intersect with the scene, we connect to a light source, compute the transport, and now if we shoot the same ray twice for surfaces, we get pretty much the same result, right? So not talking about sampling and multiple light sources, yada yada, just same ray, pretty much same results. It's a pretty deterministic result. But if we now add volumes to the mix, we shoot the ray into the scene, and now we may collide with the volume, and we compute light transport with the light source. But if you shoot the same ray again, we might actually miss the volume completely, right? So it's exactly the same ray, same pixel, same direction, but we get a different result. We do that again, we get another different result. This time we again hit the volume, but at a different point along the ray, right? So that's due to the sampling being stochastic. So each ray samples the scene, and some of the rays may actually hit the volume, some rays may not, and the position where you actually hit the volume is determined by the sampling, so it changes every time. And that's true not only for primary rays, it's also true for secondary rays, which turns into a pretty hard sampling problem. This is also, again, why we need to rely on denoisers in order to make it work. And also on a high level, the idea of denoising is to reduce the computational cost of getting like a nice looking image. Instead of just sampling over and over and over again, we use a pre-processing filter, which might be a neural network, might also be a handcrafted filter, to go from a noisy signal, which is pretty fast to compute, as close as possible to a converged solution, which is very hard to compute and takes a long time to get there. And this is approximate, right? So that's adds bias. So it's not an unbiased solution because we just guess what the result could be, but we get there much faster. Right. So let's go over a bit of previous work in the realm of denoising. There has been literally a ton of work on surface denoisers. And for example, one of these works is the spatial temporal variance guided filtering. I need to be careful what to say now because the author is a paper chair. And essentially, what it does is it uses a handcrafted filter, and it comes up with a lot of heuristics when you want to stop the blurring, right? So it filters both spatially, also temporally. And for example, one of these edge stoppers could be normal deviation. You don't want to blur over like an edge in the image, or depth deviation. Also uses variance to further guide the filter, but it needs a lot of tweaking, right? Because you need to come up with a good heuristic, both for the filter, also for temporal reuse. Another work which goes into the realm of neural denoising is from Bacco and colleagues, and their idea is to, as we heard before, not try to come up with a bunch of heuristics, but to give the yield the job to a neural network. So use a data-driven approach, and in this case, the result of the network is not the final color you actually see on the screen. The result of the network is a filter kernel that is predicted per pixel, which is then applied to the image, and the result of the filter operation is a denoised result, right? So the network comes up with a filter that is perfect for each pixel. You apply the filter, you get a denoised result. And the same idea is taken a bit further by Hasselgren and colleagues, and they essentially added a temporal recurrence loop to this idea. They also filter on multiple mipmap levels to get a large filter footprint while keeping the runtimes low. And they also added adaptive sample map, but we're not going to focus much on that for our use case. Talking a little bit about work on the volume denoising side, right? Because we want to unify both. And there has been work on volume denoising, but it's way less than for surface denoising. There has been work, for example, in the medical domain for denoising visualizations of CT scans. There's also work in more classical computer graphics context where you want to render clouds. And usually these kind of works only deal with one volume inside an environment map, so it's pretty like simple scene. And you only look at volumes in isolation. The general idea is to reuse ideas from the world of surface denoising, because we know how to do that, and try to apply what we can to volumes. But there's obviously problems, right? Because volumes are, as I said before, stochastic. The auxiliary features might be noisy. You don't even have normals and stuff like that. So there's further work as well to try to find the best set of auxiliary features for volumes, for example, by saying it out. Talking about auxiliary features. So all of these works that I just presented use auxiliary features in one way, right? They use normals, they use depth, whatever, or try to do something similar for volumes. But there's a big difference between those two. If we go back to the previous slides, right, for surfaces, the features are well defined. We shoot two rays to the same pixel, we get pretty much the same result. We have a well-defined normal, we have depth, we have albedo, we have roughness, you name it. You can use whatever you can come up with as a feature guide. But for volumes, we don't have that luxury, right? So it's stochastically sampled. What is normal in a volume? Doesn't really make sense. Depth is fuzzy because each sample, each ray has a different depth. Sometimes you penetrate deep into the volume, sometimes you collide early, sometimes you completely miss the volume. And what do you do if you average over multiple samples per pixel and you get like average depth? And that's also not a really good feature, right? So now turning towards what we propose, what we are trying to do. And with that in mind, we try to turn away from the idea of relying heavily on auxiliary features. So instead, what we want to do is we want to focus on demodulation, right? We want to split the signal into different parts. And essentially what we get is we get a diffuse channel. So we have the diffuse illumination on top and the albedo below. And the second column is the same essentially, but for specular, right? Because you have slightly different, usually as more high frequent information, the specular, low frequent information, the diffuse. You want to denoise that differently. Same idea, split between surfaces and volumes. So we have this part is the surface part, but we also have the volume part. So the volume illumination itself is on the third column. What we also want is to find the transmittance along the primary ray. This is the signal here. And the transmittance essentially defines the probability of hitting a volume versus hitting a surface, right? So if the probability is 0, at the transmittance is 0, you have a 100% chance of hitting the volume, but a 0% chance of hitting the surface behind it, and vice versa. So essentially, the energy between these surface buffers and the volume buffer is defined by the transmittance. So if it's the transmittance is great, 0.5, for example, 50% of the rays hit the volume, 50% hit the surface. In order to get that, we need to continue the primary ray, because the primary ray usually scatters in the volume, but you want the transmittance up until the surface behind the volume. So we have to continue the primary ray if we hit the volume. The same is also for the normal guide, which is essentially the only classical auxiliary feature we use. And for example, you wouldn't be able to see the street here because it's mostly occluded by the volume. So we have to continue the primary ray as well in order to fill that feature buffer. For the emission, we just pass it through essentially. We assume that emissive direct light sources, for example, are not noisy. And then we finally have the set of motion vectors, which is for surfaces, again, pretty well defined. We know we get pretty good motion vectors we can use for reprojection. But in the volume, it's a different game, right? Because how do you define motion vectors in the volume? And if anybody has a very good idea how to do that, please come talk to me after the talk. But what we essentially end up doing is we only reproject camera motion, right? Because we have some sort of depth in the volume. We use the minimum depth of all multiple samples in the volume because we want to minimize the parallax error. If you move the camera and you have like a pretty deep sample in the volume, you get a big parallax error when you reproject. So that's why we use the minimum depth for reprojection, and then we can do some sort of reprojection in the volume, but it's always going to be with error, right? So, but it's better than nothing. And as I said, we use the transmittance to split between those, and then we can also use that to combine these two, the surface and the volume parts after denoising, right? So if we now look at the overall pipeline of the denoiser, the main idea or the biggest performance increase we get in terms of quality is if we split the denoiser between surface and volume parts. Because for, again, reiterating here, for surfaces, we have well-defined features, we have good normals, we have good depth, and so on. So we can use that for denoising. We want to use it for denoising because we get a good increase in quality. However, for the volume, we don't have that, right? And we want, for the volume denoiser, don't want to add features into the mix which are not useful, which may be useful sometimes, but again, for the surface part, we don't want the surface denoiser to be bothered with any volumetric stuff. So it can focus on well-defined features and how to denoise those. And as I already said, we then finally composite the 4 different buffers. So we denoise the diffuse, the specular, the volume, and also the transmittance. And then we use the denoise transmittance to composite all these 4 buffers again for the final result. What you can also see here is that we have temporal recurrence loops. So for all of the 4 buffers, for the surface part, also for the volume part here, we reproject and then feed it back into the denoiser. And I want to talk a little bit how we did that part. So in the beginning, we also thought about using a bunch of heuristics, right, to find a good function that tells us when is the sample still useful, when is the sample stale, do we want to have it, do we want to discard it? And we found it extremely hard, especially for the volume case, to find a good heuristic that does it for all cases. So again, as we already heard today in the keynote, if there's a bunch of heuristics, it's a pretty good idea to try to replace it with a neural network, right? Because then you only have the image loss, and that's the final result you will see. You compare the image loss, and then you back propagate towards the weights and update them using stochastic gradient descent, or to get a good function that fits well for the case, and especially for volumes, right? Because reprojection in the volume is always bad. There's no good way of doing reprojection in a volume. So doing that in a kind of a lazy way, but only based on the image loss, we only care about what actually works, is a good fit for the volumetric case. So to go through the figure here, we have the 4 buffers we want to denoise as rows. And then we have the warped history in the first column, the new input, 4 samples per pixel path traced data demodulated in the 4 channels. And then we use the temporal weight in the middle. in order to determine which of the history data we want to use or which one we drop. In this case, red means we drop the history, and blue means we keep the history. So we also find stuff like this, occlusions like this. We want to drop the history because it's not present in the history. And then we blend the history together with the new data and denoise it and present it on screen. Right. So coming towards the evaluation. We always evaluate on clips, right? Because we have the temporal recurrence loops. We always want to evaluate our system on a sequence. And we use 4 different scenes. For one, the classical Cornell box, everyone knows. But we put the volume in, and the volume itself is also animated, right? So the volume is moving. We not only move the camera, we also move the volume and also some light sources. Then we have the sun temple scene as well, for example, the bistro scene, also with all with an animated volume. And for the bistro scene, we also test it with enable light sources in order to check for ghosting and similar artifacts. The different algorithms we test is the open image denoiser, so neural denoiser, without a temporal recurrence loop, without the feature guides, and with the feature guides. That's also the slide we saw in the beginning. Then we have the hierarchical kernel prediction denoiser, so a neural denoiser, but with a recurrence loop. And this one was designed for surface, and this one is designed for volume data. And then we have ours on the second to last column. So regarding about the qualitative results, these are results in dB PSNR at 4 samples per pixel input. And as we can see, on scenes with both surfaces and volumes, we're able to outperform all of the state-of-the-art denoisers we tested against. And so it's a specialized solution for this kind of scenes, right? And we also see that the temporal recurrence loop is quite important in terms of quality here, because the biggest jump from quality is basically between the neural denoiser without temporal recurrence and the neural denoiser with temporal recurrence. And it's also very important to ensure temporal stability, which, for example, we can see here. So we want to look at everything in motion. We, again, in the top row, have the input, ours, and the reference. And down here, we have the open image denoiser, which is not using a temporal recurrence loop. And we have a hierarchical kernel prediction denoiser with a temporal recurrence loop. We now play it, and it's, again, choppy, unfortunately. But you can still see that the images below here, they're flickering a lot. You can also see the problem of the over blurry result here. And here we have the background shining through, and that's the same for both, for each surface denoiser that uses features. But we're still able to faithfully recover this scene. Right. So you're probably all not only interested in the quality, probably also interested in the runtime of this whole thing. And I'm going to focus on the denoising side of things. And we evaluated everything at 1080p resolution and at 4090. And we have 2 different variants we want to show here. So what we saw before is the top row here, which is essentially the pipeline I showed, the 2 distinct denoisers. We had 2 different units, 2 different kernel prediction modules. And the unit is definitely the most chunky part in terms of runtime. Right? So evaluating the units, we also made it in shaders. It takes 5 milliseconds roughly. And the kernel prediction module takes about 1 millisecond. So what you also tried is to, going back to the pipeline figure here, is to merge these 2 units. So we only have 1 unit, so we save about 5 milliseconds of runtime, but we don't get that distinction between a volume denoiser and a surface denoiser, so they cannot specialize as well on the data. So we lose quality, but we gain some performance. And the quality loss is again, dB PSNR here. So it's between 0.5 to 2 dB PSNR of quality loss on our scenes that are all averaged results over the whole sequences and all scenes. But we can trade quality versus performance here a little bit. And I'm not talking about the renderer too much. If you're interested in the details of the renderer, there has been a fantastic keynote at both HPG and GTC last year. And there is a lot of details on the renderer. But I just wanted to say that for 4 samples per pixel, including the denoiser, we were able to stay above 30 FPS in all the scenes we tested. So it is running interactively and at real-time rates. We also implemented all of that work in the Falcor research framework. So now what we see here is actually running interactively in the research framework. So we have the test scenes again. And if I play it, it's going to be choppy again, of course. But the thing is, what you can see here, we can actually start to modify the scene, right? We can change parameters like the volume albedo. We can also change the lighting interactively. Or we can also change the thickness of the volume because it's all running interactively. And we can modify the scene and instantly see the changes. We also briefly tried a volumetric emission. You can see in the bottom right here. But I have to say that this example runs at 16 SPP instead of 4, because we don't have a dedicated system for emission. We just slapped it on top of our system. We didn't even train for it. So in order to resolve the emission, you can see that the flames are lighting the scene. And in order to faithfully recover that, we need more samples. But we were actually able to make it work. Right. So finally, to sum up, we learned that auxiliary features is the main difference between denoising volumes and surfaces. They're well-defined for surfaces, ill-defined for volumes. In order to deal with that, we want to demodulate and separately denoise both of the signals. And finally, composite the results using the transmittance, which is also denoised. And we have two options, essentially, having two individual units for the highest quality, but a bit slower runtime. Also, we could use a shared unit for more performance, but slightly degraded quality. And we were able to handle emission. However, there's a lot of potential for optimization, so we don't even have like a dedicated sampling strategy for emission. We just collected along the paths that happen to pass through the emissive volume. So that's why we need more samples at the moment, but we see potential for improvements in future work. Right, so with that, thank you for your attention. I'm happy to take questions.
Thank you very much for the nice talk. Do we have questions? Yes, in the back.
Hi, thank you for the talk. It was really interesting. I was really interested to see the performance improvements with the shared networks there. I'm curious if you have any thoughts or plans for how to get the runtime down even further from there, or if you're kind of settled at the 7 milliseconds as being the lowest you can get.
So there's definitely more potential for improvements there. For example, the shader we use to evaluate the network is, I think, 2 generations of GPUs older. So there's definitely more potential for improvements. However, this is essentially just a research prototype, right? So it's very early days. It's the first step in this direction. And I think there's way more performance to be had. But for now, for the research prototype, I think we're quite happy with the performance. But again, there's way more to expect for sure, using a lot of engineering and magic.
Hi, me talk. For the shared unit, is it the same size as the individual units? Okay.
We also try to make it a little bit bigger, so to have like a respective, to have the weights, the amount of weights similar, but you don't get a big quality increase, right? Because you want to have them separate, so you don't bottle one of the units with the features and the other one with the volumes. So it doesn't really help to increase the size of the unit itself. As soon as you have one unit, you lose quality.
Great work. So the question about the temporal projection. So you said that you use the minimum depth, right? So does that mean that for the 4 samples, you take the one with the minimum depth? So in my previous work about volumetric register, I use the RS to resample. Like I try to choose one from that has the biggest past contribution, right? So I wonder if you could consider comparing this against your current method to see if you can get the better quality.
That's a good question. I think there's definitely way more to be done regarding volumetric projection. That's a very simple way of minimizing the error, and especially sampling for the highest contribution of the 4 samples, for example, is probably a pretty good idea. However, in our situation, our approach, there will always be an error, right? Even if you pick the best sample, you will make an error during the reprojection. So we have to fix it somehow or the other. And so essentially that's why we picked that type of reprojection. So we wanted to like, finding heuristic is not possible. So we need some way of fixing it. And I think there's definitely way more to be had in terms of quality. But what we tested, trying different results, different depths, average depth, median depth, whatever, we didn't see any difference in the results. So yeah, there's probably more to be done, but I'm not sure if that's the best approach there, because it will eventually get fixed by the network.
More questions?
Hi, great work. Have you tried to have one network by providing two types of input, volumetric and surface inputs?
Do you mean like grouping the inputs into two?
Like having just one network, but have the buffers for volumetric, for surface, etc.
But then you would, okay, so if I understand it correctly, then we would need to evaluate the network twice, right? But if you have one network or?
Just one network.
But you evaluate everything at once.
Yeah, just for there.
Yeah, that's what we did with the shared network, right? So we put everything into one network and then use the features that the network outputs to predict the filters. And that's where we lose the quality because we mash everything into one and we want to divide it into two.
But even if you separate, like have buffers for volumetric, buffers for.
So that's what we do. That's what we do.
All right, one last question.
Would it work for Nerf?
I knew that would come. So the rendering itself for rendering volumes and for the GI context is quite different to NERFs, right? Because the NERF, if you look at the NERF as a GI volume, it's a flame that happens to burn at exactly the intensity that makes it a light map. So it's a weird volume, and you don't want to bounce around in the NERF because then you double count the emission of the NERF. So it's a weird one. Maybe you can use some of the ideas from this volume rendering world to accelerate NERFs, but you cannot basically plug them in one or the other. So for rendering NERFs, you would need to stop bouncing around, but then also the lighting is fixed, right? So
I actually had a serious question. What's the receptive field of the unit? I have no idea of like how much neural network compute is being like used to predict these denoising filter kernels. So if you just have like any ballpark numbers that lets me calibrate it with the stuff I've done in the past.
yeah, so the main idea is if you predict like a 64 by 64 filter, it's not going to work. It's going to work, but not in real time. So the idea is for the hierarchical kernel prediction is to denoise on whatever MIP levels instead, right? So you have small filters. I think it's 3 by 3 actually, but then you use it on multiple MIP levels, right? So you use 3 or 4 MIP levels. I think it's 3 for the surface, 4 for the volume. And then you get a essentially way larger receptive field with keeping the filter count or the filter you need to evaluate quite slim.
Right. Thank you.
All right, let's thank the speaker again. All right, next up we have Hugh Han, who works at the Korea Advanced Institute of Science and Technology. He will present his work on pixel-wise guidance for utilizing auxiliary features in Monte Carlo denoising.
Okay, so hello everyone. This is the second talk about the denoisers. Thanks for the amazing first talk. Anyway, so I'm Kyubom Han, and I'm from KAIST, South Korea, and I'm going to present our work to how to effectively utilize auxiliary features for Monte Carlo denoising. Let's first briefly talk about Monte Carlo renderings first. And we all know that they all rely on a stochastic and unbiased method called Monte Carlo integration, which provides good approximation for global illumination. But this method requires lots of samples to better approximate the pixel colors. So using thousands of samples or pixels takes too much time. So we can use few samples and we can render a frame faster, but the color will get inaccurate. And if we use extremely few samples, the rendering is done in a few seconds, or even with an optimized renderer, a real time. but with a severe noise. And we call this noise a Monte Carlo noise. So the recent works focus on applying deep learning to deal with the noise, and they train a neural network that can reconstruct a noisy image into a clean image with a lot of training data. And then the trained neural network denoises the noisy image in a short time, accelerating the whole rendering process compared to using a lot of samples per pixels. So, and during denoising, we can use auxiliary features, which can be easily obtained during the rendering process. Among various types, the most common and the most popular choice will be geometric features or the G-buffers. These G-buffers contain 3D geometric information of the first bounce of the rays, such as textures, albedos, normals, and depths. While they provide strong geometric constraints for denoising, they often fail to reconstruct and capture complex lighting effects. So the more recent works addresses this problem by proposing path features or P-buffers. And P-buffers contain light and material information of each bounce of the sample, which are helpful to reconstruct complex lighting effects such as multiple reflections, caustics, and more. But however, recent denoisers, most denoisers utilize auxiliary features by simply concatenating them to the noisy image and feed them to the neural network. And we found that this limits the utilizations of the auxiliary features and fails to take advantage of utilizing various types of them. So for instance, I wish you can see the differences. And for instance, denoising with G-buffers, the most left one, shows good reconstruction onto sockets, geometric details like sockets. And denoising with P-buffers only shows better construction under reflection, such as the hidden wire in the back. But unfortunately, using both auxiliary features using current methods does not show good reconstruction on both details. On these cases, it fails to reconstruct the reflected details better than using the P-buffers only. So our work overcomes such a problem by better utilizing both kinds of auxiliary features. Our work provides a novel guidance framework that can explicitly guide which auxiliary features should be utilized for denoising in a pixel-wise manner using ensembling weight maps. So in this scene, our framework effectively reconstructs both geometric details and the reflections thanks to the pixel-wise guidance. So before going over our method, I will briefly summarize the related works about it. Let's first talk about the utilizations of auxiliary features for learning-based denoisers. So recent learning-based denoisers analyze utilizations of various auxiliary features based on the loss convergence during training. So there will be various combinations of auxiliary features, and among those combinations, the one that shows best convergence is considered as the optimal choice. But however, such training loss using the total image loss fails to capture fine-grained information on how auxiliary features are utilized in a local manner in the image. So achieving those fine-grained information is important for our work. And for that fine-grained information, we got the idea from recent ensembling-based method for Monte Carlo denoising. And this work aims to reduce the bias in the denoisers by ensembling the results of multiple denoisers or the pair of noisy input and the denoiser results. So instead of this, we use the pixel-wise ensembling approach and to provide the pixel-wise guidance of utilizing auxiliary features for denoising. And also, unlike previous works, we provide an in-depth analysis on jointly training the ensembling network and the denoisers for a more advanced guidance. So now I'm going to demonstrate our method. And first, we have two streams of denoisers, each filtering the noisy image with only one type of auxiliary features, G-buffers and P-buffers. And we use KPCN, kernel predicting convolutional networks, as our baseline network. However, we can use various pixel-wise denoisers or even real-time denoisers as baseline. And then the ensembling network gets the two denoise results and the auxiliary features to estimate ensembling weight maps. And then these assembly weight maps are used to ensemble the two denoise results, which will be the enhanced final results of our framework. And this is overall flow of our framework. And then I'll talk about how to train our framework. The first, we train our framework in two steps. First, we pre-train the individual denoisers based on the strategy of the baseline. In this case, we follow the strategy of KPCN, which we simply train with the L1 image loss. And then to train the ensemble network, we jointly train the assembly networks with the denoisers based on using the image loss of the final ensemble image. And the red arrows show how the gradients flow from the final loss to the ensemble networks and the denoising networks. And the reason why we joint train these networks is because we can provide an enhanced pixel-wise guidance to the denoisers. But first, during training with the L1 loss of the final ensemble results, we can calculate the gradients that will flow to each of the denoisers. In this case, denoisers using G buffers DG. And here, the corresponding weight maps, WG, masks the gradients, only leaving signals where G buffers are important for denoising. And for instance, under scene with various geometric details, the denoiser DG will get signals on the regions where these geometric informations are important, such as these edges and textures, which are highlighted on the weight maps. And for the results, the joint trained denoisers will have less error on those highlighted regions compared to the pre-trained one. And the same phenomenon happens for the denoiser using P buffers, DP. On this scene, there are various types of reflections going on, and DP will get training signals on where light propagation informations are important, such as the reflection of the bottom. And similarly, the joint trained results will show less error on those regions compared to the pre-trained one. And empirically, our joint training strategy have shown best results compared to other training strategies, such as fully training the whole framework at once, or first pre-training the first denoisers and then fix them while training the ensemble network. So this is the overall I talked about how to train our framework. And I'll go over the results and the discussions of our framework. And we compared our work with the baseline denoiser KPCN using G buffers, P buffers, and both buffers. And our framework outperforms the baseline denoisers in all noise levels from 2 to 64 samples per pixels. And also our framework outperforms the baseline denoisers in terms of efficiency. And we can see that our framework takes half the time to reach the similar denoising performance compared to the baseline using both buffers. And for some examples for perceptual results, our framework can better construct the geometric details of the pasta in the kitchen scene compared to the previous work. So this is the result of previous work, and our work can effectively reconstruct these edges on the pasta. Like this. And also for the complex lighting effects, our framework can better reconstruct these reflections on the bottom of the car. There should be reflections here. These are the reference reflections. Our work can better reconstruct those details at the bottom of the car, which are reflected on the ground. And for more discussions, interestingly, we found that our framework effectively utilizes both buffers in a complementary manner. And for extremely low sample counts, the P buffers, the path features, tends to be very noisy because the light paths cannot reach the light source. So in this case, reconstructing using P buffers often shows worse reconstruction compared to using G buffers, even though the scene contains various reflections. However, with an abundant number of samples, such as like 64 samples per pixels, using P buffers shows better reconstruction in this case. However, on both cases, our framework gives more emphasis on better reconstructed results. For low sample counts, our framework gives more emphasis on results on G buffers. On the other hand, our work gives more emphasis on P buffers. So as a result, in both cases, our framework successfully ensembles the results and produces the more enhanced one. And we also compared our work with existing ensembling denoising works called ED, which uses optimization-based approach instead of deep learning. And our work outperforms this optimization-based method, which is because optimization method has to adapt weights on each scene. So anyways, our work outperformed it on all noise levels and in terms of efficiency also. This shows that using deep learning is more powerful and efficient in this case. However, there's a main limitation of our framework I would like to discuss about today. Is that our enhanced performance comes with an additional computational cost, which is not good for interactive rendering. In this case, and this is due to because our framework requires 2 passes in denoisers and assembly networks. So our work is less favorable in low sample counts in terms of efficiency. Our review is going to show that potential of how to overcome the limitations here. And so to see the relationship with the computational cost, we reduced the learnable parameters of the whole networks into half. And the reduced framework shows better efficiency in extremely short time budget and in the low sample counts than before, but with a degraded performance on all noise levels slightly due to the using few parameters. But a more sophisticated approach to reduce the computations while maintaining the performance, such as the recent pruning and sampling methods, deep learning methods, might benefit our works in terms of efficiency. So I would like to finally summarize my presentation. So our work proposed a denoising framework that provides explicit pixel-wide guidance of exploiting auxiliary features, which can enhance various denoisers to utilize various types of auxiliary features. And our work can be applied on various deep learning-based denoisers, which we can plug into our framework with a simple modification and training. And like our work can be improved with sophisticated pruning and sampling methods for reducing the computation while maintaining the performance. And you can go to the QR link to get our papers, presentation slides, codes, and interactive viewers of our supplementary reports. So thank you.
Thank you very much for the interesting talk. Do we have any questions? No questions? All right, then I'll start with one. So we've seen in the previous talk, like how basically volume and surface denoising has been split apart. How do you think, like, would the volume denoising fit into the framework? Is there something that could be naturally extended in this ensemble?
Yeah, I think it can be naturally extended because like our work just simply focus on using general auxiliary features, but for volume rendering, we need a different kind of auxiliary features, right? And as the previous presenter told us, we can decompose the scene with various effects and tackle each one. And while compositing, we can use our framework also for for enhanced compositions of these different effects, I think.
Thank you for the very interesting talk. So I'm not your area, so I guess I will ask some more layman questions. So I find it very interesting that you mix the G and the P buffers together. So do you envision there are other ways to fuse them together?
I mean, other ways to fuse.
Yeah. Do you believe there are other ways to fuse them together in such a way that you can foresee their even better performance or anything like that?
Oh yes, mainly like we wanted to extend our applications to sample-wise denoisers, which means we don't denoise in the level of pixels, we can denoise in the level of samples, but our work doesn't show the results of that. But we can also extend in those kind of sample space denoisers also. And there are various kinds of auxiliary features, like the previous presenter mentioned, the volume renderings kind of stuff, and we can extend to that. And for a more different ensembling approach, we can like the kernel the denoising methods using denoising kernels. We can use that kind of a kernel-based approach to effectively ensemble the two denoise results, I think.
Any other questions? I have another question for you. So you were saying that you have issues that performance drops a bit because you have multiple denoisers. So I was wondering, like, would you also be able to put like cheaper, like hand-forward non-neural denoisers into this ensemble framework in there? Where is it like do all of these denoisers have to be like fully in neural network?
Oh, just for assembling the results, we don't need the neural networks for denoisers, but like as you mentioned, we can enhance the final result by jointly training the whole thing, the denoisers. So to get the benefit, I think it'll be better to use the neural denoisers.
Okay. Thank you.
Thank you.
All right, let's thank the speaker then again. All right. Next up, we'll have Yannis Polykratis from Rutgers University in Essential Labs. We'll talk about an interactive framework for visually realistic 3D motion synthesis using evolutionary-trained spiking neural networks.
So thank you very much for the introduction. This is probably going to be different from what you have seen up to now, so please bear with me. This work is the last work that I did during my PhD at Rutgers while I was working in Accenture Labs. And as the title says, what we did is we drew inspiration from actual biological networks that control motions in primates and rodents. We used an algorithm, an evolutionary algorithm, to train those networks so that they can capture and learn the motion dynamics. And we applied them to animated motion synthesis. So I will start with an overview of our work. So what we did is that we had an original motion in hand, and what we wanted to do is capture these motion dynamics of the joints and the limbs, and then reconstruct the original motion as closely as possible. And at the same time, being able to transfer the captured motion dynamics to other motion sequences with similar dynamics as well, in terms of scale of movements and speed. So in addition to that, what we wanted to do is provide an interactive framework so that somebody who is not aware of spike neural networks or doesn't want to bother can play around as a designer and specify a motion and be able to see how the motion changes in real time. And in that way, with our interactive framework, we can have the original motion sequence, we can edit it, and then we can get the modified version in real time. So the motivation of the work is clearly the challenge of synthesizing animated motion. So the problems, the difficulties of such a task come from its dimensionality. So we have high numbers of degrees of freedom so that we can simulate motion in a realistic way for realistic agents. Then the variability, in other words, the same motion can be performed with completely different dynamics from different agents or even from the same agents in different contexts. And lastly, the complexity of the motions themselves. Like if we try a backflip, I cannot do it. So why would an artificial agent do it? So the go-to method is clearly reinforcement learning, and it has been demonstrating remarkable results where an agent is acting on the environment, it collects the rewards of its actions and observes its state in order to generate its new targets or goals. And as we said, there's no other argument against the results that these kind of methods have already demonstrated. But they do have their own limitations. So in general, they require very long training sessions with hundreds of thousands or even millions of episodes. And this introduces considerable power requirements during training. And lastly, the behavior that you might end up with, for example, as you can see the quadruped in the last trained state, is not necessarily as realistic as you would expect, because you need to tailor the rewards properly so that you can get the behavior that you had in mind. So, sorry. The question that other people have asked before us is, can we do something else beyond a task-agnostic method that starts to train a motion sequence from scratch? And the answer has started pretty long ago for physics-based models, where these models exploit that physical realism. If you obey the laws of physics, you are destined to get a motion that appears realistic. And the problem that these methods have is that as you increase the degrees of freedom, the complexity of the method increases exponentially. So the answer, at least one intermediate answer to this problem, comes from introducing space-time constraints. So intermediate poses of the movement that you want to reconstruct that are used as guides, and then you're trying to approximate the intermediate motion as an interpolation problem between those poses. And then the problem starts being that you need to manually specify these intermediate puzzles. So this becomes tedious, especially if you're a designer. The solution to this problem comes from human motion capture data. So we have been using this technology for years now, and sensors that are placed on specific points of human bodies can be used in order to track the movements, and they can generate the intermediate pauses. And in fact, they generate a continuum of intermediate pauses that then we can use so that we can train our methods and learn the motion dynamics. So from the motion capture data, as we said, we had that continuum of points. We need to go one step backwards now and sample the important points that we will need to use in order to perform the reconstruction. And there have been several methods that were proposed for this kind of combination of the intermediate samples into a continuous motion. Spline interpolation is the simplest and one of the most effective ones because of the simplicity and the performance. But PD controllers have been used as well. And the problem with the existing methods is that they completely disregard the spatiotemporal dynamics. You don't know what else you have beyond the dots that you want to connect. But the way to connect the dots can be variable. So what we aim to do is find a way to draw inspiration from a biologically inspired controller and then apply this kind of method to connect the dots in a way that humans do it. So digging deeper into this biologically inspired controller, our goal is this inverse problem. Given a motion sequence, can we craft the controllers that give rise to this motion sequence? So for this inverse generative problem, we would like this process to be automated. Give us the sequence with the intermediate points, and we will give you a controller for each joint that will mimic the dynamics that you have in the original motion. So there are two steps that we need to take in order to solve this problem, or at least tackle it. The first thing is a genetic code. So we have different motion dynamics, and we need to be able to generate controllers that can produce different dynamics. And therefore, we formulate a genetic code so that we can produce the different controller architectures. And the second one is we need to specify which is the best performing of these controllers. So we need to search through our space of controllers provided by the genetic code and select the one that performs best for our given task. The inspiration for the design of the simplest controller comes from biology, actual biology. And the controller that we had in mind when we started this is the controller that drives smooth reaching movements, arm movements, or front feet movements in rats. And the corresponding neuronal networks that drive these motions have been characterized not only in rodents, but also in primates and humans. So there is this continuity through evolution. And since these networks have been characterized in the deep biological context, they have also been approximated in silico with spiking neural networks so that they can reproduce this type of movements in the videos are not playing. Oh, they are playing. Okay. So they can reproduce this kind of motion dynamics with robotic arms. We wanted to reconstruct such a smooth motion that our arm would provide with a robotic arm. And this has been done in a previous paper that we had in 2023. And we get this kind of behavior where the motion starting from point A to get to point B is initiated gradually so that we don't have a jerk in the first stages when the error is large. And it also decelerates gradually towards the end of the motion so that it cannot harm some collaborator of the robot. Now, as we said, the characterization of these networks gives us one controller with a specific set of dynamics that was of interest for this specific type of movements, smooth reaching movements with our arms. What is the building block of this controller? The building block is a spiking neuron. So it's not the continuous neuron that we have been using in artificial neural networks for years. It's a neuron that behaves as the neurons in our brain and our spines, and they have a continuous membrane voltage where they encode their inputs summated through their synapses. And when that voltage exceeds a threshold value, the neuron emits an all or none binary event called spike. The input spikes are aggregated in the membrane voltage, as we just said, and then when the crossing of the threshold happens, an output spike is produced by the neuron. So the properties of this computation paradigm is that first, it is event-based. The neurons communicate with each other using discrete events, the spikes. And secondly, it is asynchronous. So a neuron communicates something to the downstream partners only when they have something to say, only when a spike is emitted, and it's silent otherwise. And these two properties provide computational benefits for this type of computation paradigm. Interestingly, I'm in a bad venue to describe this, but in addition to GPUs that NVIDIA, AMD, like Intel as well, have been producing for decades now, there's a different cohort of hardware that is optimized for simulating spiking neural networks using these two key properties that we mentioned before, event-based computation and asynchronous communication. So this is called neuromorphic hardware. There have been different chips that have been proposed, and there are different iterations of them that are getting better and better. And they provide extreme energy efficiency and low latency for different tasks. And the tasks that target neuromorphic hardware are mostly robotics, so that they can exploit these computational benefits. But we hope that there can be others that will also that will also benefit from the provided advantages. So as we said, we have a controller that has been proposed for a specific motion with specific dynamics. The question is, how can we generate architectures that will provide motions with different dynamics, not necessarily smooth motions, because not all our joints behave in the same way. Not all our muscles are built the same, don't have the same size. So in order to do that, we went on to kind of abstract the biological details of the controller structure that we just showed with a genetic code, a context-free grammar that is able to produce such controller architectures. And I will not dig very deep into this, but the idea is that the first couple of rules generate this overall general structure of the controllers. As you can see here, we have an input, the desired target angle for the joint, and an output, the current state of the joint. And there are two pathways, one that increases the control variable towards the target and the one that decreases it. And with this general structure, there can be this general structure that is defined by this first set of structure rules can be extended further by the remaining rules in our grammar that provide different motion dynamics and can enrich the computation. So with this kind of grammar doing its job in the background, we can generate the simplest controller architecture that you can see here, which is equivalent to a P-control, if somebody is more aware, and more familiar with control theory. And they can also generate the most complicated controller that we showed before, which has a smooth initiation and deceleration of the movements. So using this kind of different controllers, we are using the grammar, we are able to produce different structures of controllers that start from this general structure that is common for all of them. And then given the remaining rules that enrich the dynamics, they can split into different families of controllers. And these families end up to final architectures, which we want to test. And we will select from them the one that captures the dynamics that we have in hand. So we generate these with a genetic code, and then we need to select the one that performs best. And the selection happens with an evolutionary algorithm, an equivalent to an A-star algorithm in the controller space, that goes through the space of the controllers and chooses which is the one that closest resembles the required dynamics. So having this, what happens in the background of our method is that we start from one simplest architecture, and then the search through the space of controllers by the evolutionary algorithm is approximating the motion, the required motion, which is the blue line here, as closely as possible with the orange line. And when we find something that is close enough, or when we exceed our search limit, then we stop our search and we decide that this is the joint controller that we require for the given dynamics. Now, our method is outperforming the conventional interpolation, spline interpolation, when we're using a very low number of samples. And the reason for that is that in contrast with interpolation that goes exactly through the red points, which are our samples, our method cares more about how the connection of the different samples happens. So as you can see, the best performing controller in our method, which is the blue one, is closer to the black line, which is the reference in the meantime between consecutive samples. While the spline cares too much about the samples, but the strict dynamics of the cubic polynomials only define one way to connect the dots. Here we provide a spectrum of different controllers that can provide a family of connections between the different dots. So if we scale up this approach to multiple joints of an animated character, then we can try to capture the motion dynamics that are originally there, and we can try to reconstruct the motion as well as possible. And this can be done for slow, small range movements like walking, but also for faster and larger range movements like a running process. And beyond that, what we did is that we could also transfer the capture dynamics from an original motion sequence, like the walking one, to another motion sequence that follows similar dynamics, like this sad walking, and reconstruct the motion with the given dynamics, the original capture dynamics, not retraining our controller on the new sequence. Since the two motion dynamics are close to each other, then we are able to reconstruct the given motion pretty well. The same thing happens for this sneaky walking. And the dynamics of the motions being the same allow us to get this reconstruction accurately enough. Now, when we are trying to reconstruct a motion with different dynamics, with the capture dynamics that are far away from the desired ones, then there is a problem here that we cannot do the interpolation in the way that we would expect in order to reconstruct accurately the movement. But this is also a transfer of the original motion dynamics to a motion with different ones. So the running that you can see that we get with our controller is something like a less fit person would run like, or an older person. And at the same time, we did the same with training on faster and larger range movements and trying to reconstruct slower and smaller range movements. You can see that this sad walking, when we have been trained on the more athletic, large range and fast movements, resembles an athlete, for example, being sad after a game. As a last thing, we were able to apply our method on actual human motion capture data and not synthetic movement as the ones that I showed up to now. And we can capture small details like the coupling of different fingers together, which is interesting when we want something that looks realistic and we cannot tailor the reward of a reinforcement learning method to learn this kind of couplings. It's kind of trickier, while the mockup data already have that information and we can approximate it. And as a last point, what we did is that we designed this lightweight interactive framework so that we can select a joint of the character that we have. And given that joint that we select, we can interactively delete or edit the key points that we use in order to reconstruct the movements. And with this kind of editing, we are getting the modified motion in real time, where in this case, we just shut down the movement of the hip joint and we can see the limp walking of the animated character. So with this interactive framework, a designer can use all this background of the generative model the generative grammar and the evolutionary algorithm without knowing the specific details of what SNNs are. So as a summary, we have provided this biologically inspired controller and a generative grammar that provides different architectures. We have provided an optimization algorithm that runs through the controller space and selects the best performing one given our task. And as a last thing, we provided this interactive framework for real-time editing of the motion. So I will conclude the talk with a question about what we could use the method for. And my idea, and I'm really happy to discuss this if anybody has something to say, is virtual reality. Like if we have a high-speed camera that is used on VR headsets these days, and it captures our hand movements in real time, then we want to reconstruct this movement in the VR headset for the person to interact with. So if we have consecutive frames of these hand-captured motion, then we would like to interpolate between the two different frames in a way that appears realistic for how people, humans, would perform these movements. So our method brings one benefit, that is that as we have like an oversampled motion sequence between frames, decreasing the frame rate considerably does not affect the realism of the movement that we reconstruct. So with a very low sampling rate, we can reconstruct the motion of a human hand quite accurately. And to quantify this, we're showing this distortion over frame rate. And what we end up with is that we can have a reconstruction with less than 15% of distortion, while we decrease the frame rate more than 70%. And if we bind this and combine it with the neuromorphic hardware, we can have the efficiency of transferring between the capturing system and the reconstruction system with considerable power efficiency when the method is running on neuromorphic hardware optimized for this kind of control methods. So as a summary again, this is what we provided in this work. And this is pretty much like the flow that we had in mind, with the real-time editing framework being something that we can give to somebody who is not an expert, either on graphics or on spiking neural networks. Thank you for your time, and I think this is all I had for you.
Very much for the very interesting talk. Do we have any questions?
Hey, thank you for the talk. As far as the last part of it you mentioned about applying it for VR interpolation, I would definitely agree with what you are saying. Anybody who's worked on Kinect technology would have really appreciated having some biologically based interpolation motion rather than just trying every frame to guess where on earth your feet came from to be behind your head now. I wonder if you tried applying the technology to retargeting, to essentially retarget your motion to a different skeleton than the one you used as reference.
Yes, we have a similar simulation. So as you know, probably the animated character that we used is from an open source library, 3JS, and it had different characters that we could use as well. So as long as there is a correspondence in the number of joints between the two characters that we have been trained on, the transfer of the dynamics can happen. I don't have the animation here, but yes, we do have that.
Thank you.
Thanks so much for the delightful talk. It's also hilarious that whenever like people outside graphics like show this different hardware architecture, it's like, wait, how did you train this? But okay, so I have a question related to the practice, and I also have a question related to just like how you got there.
Sure.
So let's start with how you got there. Can you describe a little bit like what it's like to work with like the spiking neural network emulator? And can we transfer this to normal technology without having to like make another chip? And also in terms of the findings. So there's this entire trend among Facebook has bought control apps to do EMG-based sensing of muscle activations in order to predict muscle pose and so on. And what you're proposing here is sort of like a different approach to capturing basically the state of activations inside our neurons in order to do prediction. I was wondering if you could talk a little bit about how far you can go there. What's the best case scenario? Can we do predictions on where the hand should go 50 milliseconds in advance? Can we actually predict further activations down the hand? Can we base some things based on gait that would tell us about what the upper torso is doing?
Absolutely. Great question. Thank you very much. And I think that I can answer both questions pretty much in the same time. So the good thing about neuromorphic hardware is that it's trying to approximate the way that the brain computes. So the two key points that I showed about event-based and asynchronous computation are actually the source of the benefits in our brain. This is how our brain can do all this magnificent computation with just 20 watts of consumption. But at the same time, if we are trying to approximate it on a hardware that is conventional, like a CPU or a GPU, then we are losing these essential properties. And the computation of a spiking neural network on conventional hardware is actually more consuming than conventional methods, like deep networks, because we not only need to have an input-output computation, which is usual for deep nets, but we also need to incorporate time. So we introduce a different dimension. We need to keep track of the neuron states and so on over time. And this introduces more and more computational overload. On neuromorphic hardware, dedicated hardware, on the other hand, is specifically designed for that. So it simplifies the process as long as you respect its key principles, computational principles. And that is the problem. Neuromorphic hardware is there. The algorithms to be using the neuromorphic hardware are still kind of missing. So this is the space that we are trying to open up. If we define algorithms that can run on neuromorphic hardware and they can use the properties of the materials themselves, then they can combine the good, like the benefits of both worlds. For now, things are still nascent. Like neuromorphic processors first came out about 2010. It's not something that is, I wouldn't say that it's new. I will take that back because technology is galloping at this point. But overall, we are still waiting for the major breakthrough for algorithmic development on neuromorphic hardware. But the idea behind the talk and the inspiration of the talk is that if we go back to the brain, which has the algorithms, and they have been evolutionarily tuned over millennia, then we already have a base of algorithms that we could use and we could draw inspiration from. And we have a hardware that is already built to support this kind of properties. So our take-home message from this is, look at the brain, look how it does what you want to do, and maybe there is a smarter solution from what we have been trying to do in other ways. And this is what I would say for the last part of your question, what is next? Yes, the prediction of motion, because here we're doing some kind of motion in betweening. We have the final and the initial points, and we just connect them together in a realistic way. But there is space for extra, prediction of next motions or the next points. So we can also do the planning. And this is something that we have trying to be following in that direction recently. But it's not there yet. But the existing methods need to be translated. And that translation process is kind of...
Is there a theoretical ballpark for how far you can go?
I don't think so. I won't say that, but I don't think so. I haven't read something, and if I had, I would have changed my direction. So I will take it with a pinch of salt, what I'm saying. But in terms of computational power, when it comes to temporal computation, then spiking neural networks are supposed to have a benefit. But you need to design them in a way that you can harness their benefits. Did I cover most of it?
Do we have any more questions? All right, then I'll have to ask, since we're in the denoising session, so can you use this to denoise motion capture data? So like, let's say you have this interpolation kernel, and each of these snapshots has some noise in the measurement of the actual joint positions. Like, would this be useful to do denoising and clean up these recorded sequences?
Yes, that's exactly what we would ideally want. So you have something that is producing intermediate positions, but because of the complexity of the task, because you're doing some kind of generalized interpolation, there is a lot of noise, jitter. So by reducing the samples that you're taking over time, you can also decrease the noise when you're sampling. And in that way, this method can connect the dots in a way that appears realistic, by also decreasing the variance in the original movements. So yeah, ideally, like, we don't have a neuromorphic version of the generation of the intermediate targets. This is something that we want to work on. But beyond that, we do have something that could smoothen the intermediate points.
Another question, so like, you're basically proposing an interpolation kernel. So have you thought of using this in like a completely different field? So like, let's say you have a very sparse sampling of an image, and like maybe there's like a genetical code of like, this is what makes an image look like an image to a human. So would you be able to interpolate between like sparsely sampled images?
That's exactly the question that I've been asking myself over the last 2 days, because I see all these like methods for images, and I was always thinking one dimension of joint angles. So ideally, yes. The problem that I see right away is that for joint motions, the way that we followed is that we know how motion dynamics work for joints. If we can have a similar decoding of dynamics in an image, like how the image texture changes across the image, then this would be easily applicable. But I don't know if it's easy, and it's definitely not easy for very fast changing environments with images, like completely different patches of images in the same part.
Awesome, thank you very much. Do we have any other questions? Right, everybody's hungry. Well, let's thank the speaker again.